Hello there everybody and welcome back to another Chem-MrT video, and this time staying with topic 5.1 about endothermic and exothermic changes in the energy changes topic, which is the overall of topic 5. We're looking at reaction profile diagrams, or also known as energy profile diagrams. This is something that you will need to do if you're doing triple and combined, so it's for both, and it's also both higher and foundation tier, so everybody needs to know this. So what we're going to be looking at today in particular is what activation energy is, what an reaction profile or energy profile diagram is, how to draw a reaction profile diagram, and what the different parts of that diagram show us about a chemical reaction. You need to be able to interpret this for exam questions. You also need to be able to draw them for exam questions. You might get asked to sketch them out. And then we're going to have a look at the difference between the profile diagrams for endothermic and exothermic reactions, and that's really easy part of the topic. I quite like it. I'm not quite sure why. I guess I just like drawing the diagrams. So before we have a look at our diagram, the basics of a reaction profile diagram are as follows. On the y-axis we have our energy. On the x-axis we have time or reaction progress, so just basically how far the reaction is progressing. The reactants go on the left of the graph, so towards the left hand side, towards the y-axis, and the products go towards the right hand side of the graph, towards the open side. The difference in the height between the reactants and the products shows us the energy difference between the reactants and the products fairly obvious, and we can also work out whether it's endothermic or exothermic from that. Okay, so these are the important parts to take away and to have a little focus on before we have a look at how to draw them. Because these diagrams are just sketches, they are not actual graphs, we do not need to put units down for energy or give values for energy or time as well. Obviously most chemical reactions happen fairly quickly, and so having time in things like seconds or especially minutes wouldn't make sense. Right, we'll go and have a little look now at drawing some of these diagrams. Here is our basic axis. We've got E for energy on the y-axis, T for time on the x-axis at the bottom. We can see E equals energy, T equals time. Now we're going to draw our our reactants on first, and we're going to use, towards the left hand side, we're going to put our reactants, and I'm going to put my reactants there. I'm going to label that R for reactants. Then down at the bottom somewhere, a little bit lower on the right hand side, I'm going to put my products. P for products. And we can see that our reactants are higher up in energy than our products are. And this difference in energy here, this change in energy, which I'm going to give the symbol delta, which is a triangle, Greek letter delta, delta E. Delta is used in science to mean change in. So delta E equals change in energy. And we can see here that this change in energy is negative. So the products have got less energy than the reactants. That means this reaction is going to be exothermic. So if the reaction is like this, it is exothermic. You can have a look at this and you can copy this down. This is your exothermic profile diagram, reaction profile diagram. Now one thing you may just see when you draw them on, and you will have to put on, is something called the activation energy. Okay, and the reaction profile actually looks like this. So first we've got to go up the hill before we can come down the other side. Okay, so we see a little thing like this, and this bit here is the activation energy. Okay, which I'm going to call EA. Okay, energy activation. So E dot A equals activation energy. You could do A dot E, doesn't matter. Now in an exam you will be expected to label up the following things. You'll be able to be expected to label up the change in energy, showing it going down from the reactants to the products in this case, and the activation energy, which is this hill here. If you don't know what activation energy is, don't worry about it too much. We're going to come on to it in a second. But basically, it's the amount of energy you need to start the reaction, get it going. Now I'll have a look at what this looks like for an endothermic reaction, because this is exothermic. So now we're going to have a look at endothermic. I'm just going to shorten to end, or endo. Now, and this time, our reactants start lower down than our products. And so now, our change in energy is this amount here. So that's going to be our delta E. Change in energy is that amount here. Okay, and this time it's positive, endothermic. And what we'll also see is we'll still see the activation energy coming up and down like this, but you'll notice this time the activation energy is significantly higher. Okay, all the way up to the top, that's our activation energy. It's significantly higher than it was before. Okay, but it's still, the overall energy change is still only this amount, because when we add the activation energy in, we add this much activation energy in, but then we get this activation energy back out again. So when you're going up, you're putting energy in. When you're coming down, you're getting energy back out. So, important part, the change in energy is just the difference between the reactants and the products. It's not the whole peak. You should be able to do a little diagram of endothermic and exothermic and be able to produce those at will in an exam. So we'll have a little look at that on two next to each other. So exothermic products have less energy than our reactants. P for products, R for reactants. In endothermic, the opposite way around. The reactants have got less energy than the products. Nice and simple. And that was the diagrams. So a little recap. Y is the energy, y-axis is the energy, x-axis is time. So the higher up you go on the y-axis, so the higher up from the bottom of the graph you go, the more energy a compound has got, or the reactants or the products have got, and the lower down, the less energy. The reactants, they always go on the left-hand side of the graph, and the products always go on the right. So even if it's a exothermic or endothermic reaction, it doesn't change that. We always draw the reactants on the left-hand side of the graph. The difference in the height shows us the energy difference. The greater the difference, the more energy difference there is. And also the relative heights tell us if it's exothermic or endothermic. So you must remember that exothermic lower down in energy than the products are lower down in energy than the reactants, and it's the opposite way around for endothermic. So in a chemical reaction, we'll just define what activation energy is a bit more here. Okay, so in order for two chemicals to react, the particles must collide. Most of the time, however, this isn't enough. Okay, so most of the time this isn't enough. You can't just have two particles colliding and have them react together. You can think about an unlit Bunsen burner. In the unlit Bunsen burner, you've got your methane, which is your gas, and you've got oxygen from the air that are rushing through there. Those particles are colliding all the time, but they don't spontaneously react. So how do we start that? How do we light a Bunsen burner? Of course, we need a spark or a flame to start the reaction. So you might use a lit splint, you might use a match. You can also use some devices that create sparks, and that will cause the reaction to ignite. And that's because that reaction has got a fairly low activation energy. It doesn't take much to get it started. You could also think, though, if you're trying to burn a log, for example, or even charcoal, so charcoal, barbecue, it's definitely barbecue season at the moment in the UK. If you try and light charcoal, it takes quite a lot of energy. It doesn't take just a spark, it needs more, so that it's got a higher activation energy. And we could probably sketch that out in a reaction profile diagram. I want you to give it a go. See if you can sketch out the reaction profile diagram for lighting a Bunsen burner and also for lighting charcoal, showing the differences in the activation energy, and we'll have a look at my answer in a second.
So here is my low activation energy and here is my high activation energy. And we can see the difference is the size of the hill, as it were. Okay, so for the low activation, small hill. Large activation, big hill. And we can also see in this example here, we have one where we've got a large value for the change in energy. So this would be something that's very exothermic. In this example here, it's giving out a lot of heat. And here we have a smaller change in energy. So a small change in energy. We can see that by the difference in the heights, relative heights of the reactants and the products. The greater the distance, the more the change in the energy.
Okay, now little definition. Activation energy is the minimum energy that particles must have to be able to react. Okay, so that's the definition. You do need to know that definition. It is specified in the syllabus, so please learn it. Now, summary, what we've done today. So activation energy, minimum amount of energy needed to start a reaction. In exothermic reactions, the products are lower in energy than the reactants. In endothermic reactions, the products are higher than the reactants, okay, in the diagrams. The height difference between them shows the overall energy change, and the activation energy is shown by a hill that rises up before falling. The greater the size of the activation energy hill, the more activation energy is needed to start a reaction. And it's important to remember you do not include the activation energy in the overall energy change, because that energy we put in and then it comes back out again. So it balances out, it works out to be a net energy change of 0. Okay, hope you've enjoyed the video, guys. Please remember to leave your questions and comments in the comment section below. Please give a thumbs up to the video. I do appreciate it. Please remember to subscribe if you've not already done so, and share the video as well. And to all my returning subscribers, thank you very much. I'm very appreciative of the views and the support that you give me.